Method of preparation of test drug. The hydroalcoholic extract of Hippophae rhamnoids, both fruits and leaves, was added with additional additive to make final capsule as 500 mg each. One 500 mg capsule contained the extract of the plant in the dose of 450 mg, 250 mg fruit and 200 mg leaves, remaining additive and concealed in empty capsule and given into 2 divided equal doses, i.e., 1 capsule morning and 1 capsule evening continuously for 6 months. Similar to test drug, placebo capsules were also prepared using dextrin powder and given to cases for same duration and in same manner as in test drug treatment group. Observation and results. It is observed that homocysteine level enhances with advancing age as compared to various studies conducted in younger age group, 40 to 50 years, of both sex. Further, the female cases have exhibited higher homocysteine level than the male subjects. Results show that at the initial level a high homocysteine level is obtained which declined significantly following Hippophae rhamnoids treatment during 6 months of study period. The differences in the values of initial homocysteine level and the values obtained at the end of 6 months are highly significant, showing the beneficial role of the test drug. Placebo-treated subjects did not show any such change. Table 1. The biomarkers, high-sensitive C-reactive protein and TNF-A measurement have also shown association with elderly people. A high level of C-reactive protein and TNF-A with high homocysteine has demonstrated the risk of cardiovascular and Alzheimer's disease or Parkinson's disease among the elderly subjects. The treatment of Hippophae rhamnoids is effective in the prevention from the above adversities to the elderly subjects, as a marked decrease in C-reactive protein and TNF-A levels are noticed during trial period. Table 2-3. The differences are significant on comparison in both the parameters in test drug-treated group. The drug Hippophae rhamnoids is also proven for its antioxidant effects in several studies. Thus, as synergism, the test drug has also helped to a great extent by reducing the oxidative injury involved with aging process. Table 1. Decline in homocysteine level following Hippophae rhamnoids treatment among elderly. Homocysteine, UML/L, comp initial versus after 6 months therapy. Clinical groups, sex, no of cases, initial, after 3 months therapy, after 6 months therapy. Placebo-treated, M, 21, 24.34 plus or minus 4.11, 23.77 plus or minus 4.34, 23.98 plus or minus 3.84, T equals 0.29 P greater than 0.05, F, 18, 28.97 plus or minus 5.01. 29.22 plus or minus 4.75, 27.96 plus or minus 3.38, T equals 0.71 P greater than 0.05, treated with Hippophae rhamnoidos, M, 24, 26.58 plus or minus 4.11, 21.35 plus or minus 3.92, 18.96 plus or minus 3.92, T equals 7.05 P greater than 0.05, F, 19, 29.20 plus or minus 4.12, 25.62 plus or minus 4.06, 20.84 plus or minus 3.72, T equals 8.15 P greater than 0.05. Table 2. Decrease in high serum C-reactive protein level following due Hippophae rhamnoids treatment in elderly people. C-reactive protein, Mg/L. Clinical group, sex, no of cases, initial, after 3 months therapy, after 6 months therapy, comp initial versus after 6 months therapy. Placebo-treated, M, 21, 4.23 plus or minus 1.31, 4.09 plus or minus 0.94, 4.62 plus or minus 0.88, T equals 1.14 P greater than 0.05, F, 18, 3.97 plus or minus 0.85, 3.82 plus or minus 1.11, 4.01 plus or minus 1.02, T equals 0.12 P greater than 0.05. Treated with Hippophae rhamnoids, M, 24, 5.03 plus or minus 1.00, 3.68 plus or minus 0.97, 3.17 plus or minus 0.84, T equals 7.15 P greater than 0.001, F, 19, 4.06 plus or minus 1.12, 3.13 plus or minus 0.85, 2.85 plus or minus 1.03, T equals 3.55 P greater than 0.01. Table 3. Reduction in pro-inflammatory marker TNFA following Hipophy rhamnoids treatment in normal elderly people. Comp. Initial. Clinical groups, sex. No of cases, initial, after 3 months therapy, after 6 months therapy, comp initial versus after 6 months therapy, placebo-treated, M, 21, 923.64 plus or minus 88.73, 982.79 plus or minus 71.02, 955.44 plus or minus 60.36. T equals 1.35 P greater than 0.05, F, 18, 897.45 plus or minus 69.11, 922.45 plus or minus 52.70, 945.26 plus or minus 78.38, T equals 1.94 P greater than 0.05, treated with Hipophy rhamnoids, M, 24. 1014.73 plus or minus 58.34. 934.87 plus or minus 61.73, 864.72 plus or minus 72.11, T equals 7.92 P greater than 0.001, F, 19, 984.33 plus or minus 68.86, 805.97 plus or minus 59.22. 762.45 plus or minus 81.04, T equals 9.09 P greater than 0.001. Conclusion. It is concluded that a number of experimental and clinical evidences are there providing that high homocysteine acts as a neurotoxin and is a major risk factor for neurodegeneration or manifesting the Alzheimer's disease or Parkinson's disease. Its role is well defined in contributing the vascular complications. Further, it also causes oxidative stress and glutamatergic excitotoxicity suggests a risk for neuropsychiatric disorders such as schizophrenia, depression, etc. The high prevalence of hyperhomocysteinemia in elderly population is warranted for a proper and safer treatment strategy to prevent them from future consequences of neurodegeneration. It is proposed on the basis of present clinical trial that Hipophy rhamnoids is a better remedial measure in the prevention and management of hyperhomocysteinemia, reducing the involved inflammatory process and also oxidative injury particularly among elderly subjects, where the synthetic chemical interventions are restricted, and thus, the risk of various neuropsychiatric disorders including vascular complications are prevented/minimized to a great extent. References. 1. Bottiglieri T., Krellin R., Reynolds E. H. 1995, Folate and Neuropsychiatry. In, Bailey L.B., edition Folate in Health and Disease. New York, Marcel Decker 435-62. 2. Bottiglieri T., Reynolds E. H., Londy M., 2000. Folate in CSF and Age. J. Neural Neurosurg Psychiatry, 69:562. 3. Chai Q, G. Xiaoyan, M. Zhao, H. Weman and Y. Zhang. The experimental studies on the cardiovascular pharmacology of seabuckthorn extract from Hipophy rhamnoids L. In, Proc. International SWMP. Seabuckthorn. Xina, China, pages 392 to 397, 1989. 4. Chern, C.L., Huang, R.F., Chen, Y.H., Cheng, J.T., Liu, T.Z., 2001. Folate deficiency-induced oxidative stress and apoptosis are mediated via homocysteine-dependent overproduction of hydrogen peroxide and enhanced activation of NF-kappa B in human Hep G2 cells. Biomed. Pharmacothor. 55, 434 to 442. 5. Dalton, M.L., Gadsden Jr., P.F., Wren, R.W., Rosenquist, Th. 1997. Homocysteine signal cascade, production of phospholipids, activation of protein kinase C, and the induction of CFOS and CMYB in smooth muscle cells. Faceb J. 11, 703-711. 6. Finkelstein, J.D., 1998. The Metabolism of Homocysteine, Pathways and Regulation. Ur J. Pediatr. 157, Supple, 2, S40, S44. 7. Folbergrova, J., Hogvikova, R., Merex, P. 2000. Behavioral and metabolic changes in immature rats during seizures induced by homocysteine acid, the protective effect of NMDA and non-NMDA receptor antagonists. EXP Neural 161, 336-345. 8. Gita, S. Et al. Antioxidant and immunomodulatory properties of Hippophae rhamnoids. An in vitro study. J. Ethnopharmacol, 79, 373-378, 2002. 9. Green, J.G., Greenemeyer, J.T., 1995. Exacerbation of NMDA, AMPA, and L-glutamate excitotoxicity by the succinate dehydrogenase inhibitor malonate. J. Neurochem. 64, 2332-2338. 10. Grieve, A. Butcher, S.P., Griffiths, R., 1992. Synaptosomal plasma membrane transport of excitatory sulfur amino acid transmitter candidates, kinetic characterization and analysis of carrier specificity. J. Neurosci. Res 32, 60-68. 11. Ho, P.I., Collins, S.C., Didavat, S., Ortiz, D., Ashline, D., Rogers, E., Shea, T.B., 2001. Homocysteine potentiates beta-amyloid neurotoxicity, role of oxidative stress. J. Neurochem. 78, 249-253. 12. Ho, P.I., Ortiz, D., Rogers, E., Shea, T.B., 2002. Multiple aspects of homocysteine neurotoxicity, glutamate excitotoxicity, kinase hyperactivation and DNA damage. J. Neurosci. Res 70, 694-702. 13. Huang, H.Y., Appel, L.J., Croft, K.D., Miller 3, E.R., Mori, T.A., Putty, I.B., 2002. Effects of vitamin C and vitamin E on in vivo lipid peroxidation, results of a randomized controlled trial. A.M. J. Klin. Neutre. 76, 549-555. 14. Huang, R.F., Huang, S.M., Lin, B.S., Wei, J.S., Liu, T.Z., 2001. Homocysteine thiolactone induces apoptotic DNA damage mediated by increased intracellular hydrogen peroxide and capase 3 activation in HL60 cells. LifeSci, 68, 2799-2811. 15. Kim, W.K., Pei, Y.S., 1996. Involvement of N-methyldiaspartate receptor and free radical in homocysteine-mediated toxicity on rat cerebellar granule cells. Neurosci. Let. 216, 117-120. 16. Kim, W.K., Pei, Y.S., 1996. Involvement of N-methyldiaspartate receptor and free radical in homocysteine-mediated toxicity on rat cerebellar granule cells. Neurosci. Let. 216, 117-120. 17. Kokame, K. Agarwala, K.L., Cato, H. Miyata, T. 2000. HERP, a new ubiquitin-like membrane protein induced by endoplasmic reticulum stress. J. Biol, Chemistry 275, 32,846 to 32,853. 18. Krumman, A. Kulm C. C. Chan, S. L. Krumman, Y. Gua, Z. Penix, L. Matson, M.P., 2000. Homocysteine elicits a DNA damage response in neurons that promotes apoptosis and hypersensitivity to excitotoxicity. J. Neurosci. 20, 6920 to 6936. 19. Krumman, A. Kumaravel, T.S., Loani, A. Peterson, W.A., Cutler, R.G., Krumman, Y. Hoffney, N. Lee, J. Evans, M. Matson, M.P., 2002. Folic acid deficiency and homocysteine impair DNA repair in hippocampal neurons and sensitize them to amyloid toxicity in animal models of Alzheimer's disease. J. Neurosci. 22, 1752 to 1762. 20. Kuhn, W. Hummel, T. Woitala, D. Muller, T. 2001. Plasma homocysteine and MTHFR C677T genotype in levodopa-treated patients with PD, Neurology 56, 281 to 282. 21. Lazarwicz, J.W., Ziembowicz's, A. Matija, E. Staffage, A. Zyminska, E. 2003. Homocysteine-evoked 45Ca release in the rabbit hippocampus is mediated by both NMDA and group I metabotropic glutamate receptors, in vivo microdialysis study. Neurochem. Res 28259 to 269. 22. Lipton, S.A., Kim, W.K., Choi, Y.B., Kumar, S., D'Amelia, D.M., Rayudu, P.V., Arnell, Dr. Stamler, J.S., 1997. Neurotoxicity associated with dual actions of homocysteine at the N-methyl-D laspartate receptor, PROC. Natal, Academic, Sci. U.S.A., 94, 5923 to 5928. 23. Matson, M.P., Shea, T.B., 2003. Folate and homocysteine metabolism in neural plasticity and neurodegenerative disorders. Trends Neurosci. 26, 137 to 146. 24. Matson, M.P., Shea, T.B., 2003. Folate and homocysteine metabolism in neural plasticity and neurodegenerative disorders. Trends Neurosci. 26,137 to 146, 25. Miller, J.W., Green, R., Mungas, D.M., Reed, B.R., Jagust, W.J., 2002. Homocysteine, vitamin B6, and vascular disease in AD patients. Neurology 58, 1471 to 1475. 26. Mudd, S.H., Scoveby, F., Levy, H.L., Pettigrew, K.D., Wilkin, B., Pirates, R.E., Andrea, G., Bors, G.H., Bromberg, L., Cerrone, R., 1985. The Natural History of Homocystinuria Due to Cystathionine Beta Synthesate Deficiency. A.M. J. Hum. Jennett. 37, 1 to 31. 27. Nagy, Z.S., Smith, M.Z., Iziri, M.M., Barnettson, L., Smith, A.D., 2000. Hyperhomocysteinemia in Alzheimer's disease and expression of cell cycle markers in the brain. J. Neurol, Neurosurg. Psychiatry 69565 to 566. 28. Ramon Diaz-Arastia, 2000. Hay and Neurologic Disease Arch Neural, 57:1422-1428. 29. Reynolds E.H. 2002. Benefits and Risks of Folic Acid to the Nervous System. J. Neural Neurosurg Psychiatry, 72:567-71. 30. Sai, X, Kawamura, Y, Kokeim, K, Yamaguchi, H, Shiraishi, H, Suzuki, R, Suzuki, T, Koichi, M, Miyata, T, Kitamura, T, Destruper, B, Yanagisawa, K, Kamino, H, 2002. Endoplasmic reticulum stress-inducible protein, HERP, enhances presenilin-mediated generation of amyloid H protein. J. Biol, Chemistry 277, 12915, 12920. 31, Cellhub J. Jacques P.F., Wilson P.W., Rush D., Rosenberg I.H. 1993. Vitamin status and intake as primary determinants of homocysteine in an elderly population. JAMA, 270, 2693-2698. 32, Cellhub J. Miller J.W. 1992, The Pathogenesis of Simia, Interruption of the Coordinate Regulation by S-adenosylmethionine of the Remethylation and Transulfuration of HCY. AMJ Clin Neutre, 55:131-138. 33, Shea, T.B., Rogers, E., 2002. Folate quenches oxidative damage in brains of apolipoprotein E-deficient mice, augmentation by vitamin E, mole brain Res 108, 1-6. 34, Upchurch, G.R., Welch, G.N., Fabian, A.J., Friedman, J.E., Johnson, J.E., Keeney, J.F. Jr., Loscalzo, J., 1997. Homocysteine decreases bioavailable nitric oxide by a mechanism involving glutathione peroxidase. J. Biol, Chemistry 272, 170121717. 35, Wall, R.T., Harlan, J.M., Harker, L.A., Stryker, G.E., 1980. Homocysteine-induced endothelial cell injury in vitro, a model for the study of vascular injury. From Res 18, 113-121. 36, Wroblewski, J.T., Nadeau, J.H., Roth, B.L., 2003.1 Homocysteine sulfinic acid and other acidic homocysteine derivatives are potent and selective metabotropic glutamate receptor agonists. J. Pharmacol. EXP there. 305, 131-142. 37, Yang B. and H. Callio supercritical CO extracted seabuckthorn, Hippophae rhamnoids, oils as new food ingredients for cardiovascular health. Proc. Health Ingrid. Europe 2002. Paris, France, pp. 7, 2002.